Hello and welcome back. In today's video, I'm overclocking the Intel Core i9-13900K all the way up to 6.1 GHz using the GIGABYTE Z790 Aorus Master motherboard and EK Quantum custom loop water cooling. As I've demonstrated already in my previous Raptor Lake overclocking guides, Intel's 13th generation core processors have a lot of headroom for overclocking. That's no different with the Core i9-13900K, though the 13900K is already pushed quite a bit out of the box. So the overclocking journey with the Core i9 was a bit different than the journeys that have so far shown with the Core i7 and the Core i5s. Nonetheless, I'll still try to show you how to tame this beast. Alright, let's get started. The Core i9-13900K is part of Intel's 13th generation core processor lineup. Intel Raptor Lake builds on top of the performance hybrid architecture introduced with 12th gen Alder Lake. So it also features performance P-cores and efficient E-cores. Like Alder Lake, it is built on the Intel 7 process technology compared to its Core i9-12900K predecessor launched 1 year ago. The 13900K has a 600 MHz higher maximum turbo boost frequency and 8 additional threads while costing about $60 less. The Core i9-13900K has a lot of automatic frequency boosting technologies on board for the P-cores. The base specification for the 13900K isn't that entirely clear, so I want to give you a brief overview. The P-core base frequency is 3 GHz. The Turbo Boost 2.0 frequency is 5.4 GHz up to 2 active P-cores and 5.3 GHz up to 8 active P-cores. Every P-core can boost to 5.4 GHz. The Turbo Boost Max 3.0 frequency is 5.7 GHz for up to 2 active P-cores. Only the favored cores can boost to 5.7 GHz. The others are limited to 5.4 GHz. When thermal velocity boost is active, the 2 favored P-cores can boost to 5.8 GHz and every non-favored P-core can boost to 5.5 GHz. Thermal velocity boost is enabled when the CPU temperature is below 70 degrees Celsius. When adaptive boost technology is enabled, up to 8 P-cores can boost to 5.4 GHz. When both adaptive boost technology and thermal velocity boost are active, up to 8 P-cores can boost to 5.5 GHz. The AVX negative ratio offset is -5. When the AVX negative ratio offset is activated, the maximum CPU ratio is the Turbo Boost 2.0 limit. The ratio is offset per core from their maximum allowed ratio, so the favored cores can run up to 5.3 GHz and the non-favored cores can run up to 5 GHz. In this video, we will cover 4 different overclocking strategies. First, we try out GIGABYTE's instant 6 GHz profile, unleash Turbo Boost 2.0 and enable XMP 3.0. Second, we try out the GIGABYTE enhanced multi-core performance profile. Third, we get into the simple manual tuning of a Raptor Lake processor. Lastly, we fine-tune our manual overclock with a couple of expert techniques. But before we jump into the overclocking, let's first have a look at the hardware and the benchmarks that we'll be using in this guide. The system we're overclocking today consists of the following hardware. I explained how I use the Elmo Labs products in SkatterBencher number 34. To make a long story short, by connecting the EFC to my EVC2 device, I can monitor the water temperature, ambient temperature, and fan duty cycle. I also use the Elmo Labs EFC to map the radiator fan curve to the water temperature. Without going into too many details, I've attached an external temperature sensor from the water in the loop to the EFC. Then I use the low-high setting to map the fan curve from 25 to 40 degrees water temperature. I use this configuration for all overclocking strategies. The main takeaway from this configuration is that it gives us a great indication whether or not our cooling solution is saturated. Suppose the CPU is at TJ max and the water temperature exceeds 40 degrees Celsius. In that case, it means the fans are at maximum speed and thus the cooling solution is saturated. Improving the cooling solution by adding radiators or changing to more powerful fans would be the right action. Suppose the CPU is at TJ max and the water temperature is below 40 degrees Celsius. In that case, it means the cooling solution is not saturated. Therefore, to improve the CPU temperature, you may enhance the thermal transfer of the CPU heat into the loop by changing the thermal paste, delidding, or changing the water block. We use Windows 11 and the following benchmark applications to measure performance and ensure system stability. Before we start overclocking, of course, we must check the performance at default settings. Please note that the GIGABYTE Z790 Aorus Master motherboard unleashes the Intel Turbo Boost 2.0 parameters out of the box. So in order for us to check the performance at default settings, we first have to go into the BIOS and switch to advanced mode. Enter the advanced CPU settings submenu. Set turbo power limits to Intel POR. Then save and exit the BIOS. The default Turbo Boost 2.0 parameters for the Core i9-13900K are as follows. Here is the benchmark performance at stock. Here are the 3DMark CPU profile scores at stock. When running Prime 95 small FFTs with AVX2 enabled, the average CPU P core clock is 5030 MHz and the average CPU E core clock is 3843 MHz with 1.133 volts. The average CPU temperature is 84 degrees Celsius. The ambient and water temperature is 26.2 and 37 degrees Celsius. The average CPU package power is 253 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU P core clock is 5290 MHz and the average CPU E core clock is 4107 MHz with 1.247 volts. The average CPU temperature is 72 degrees Celsius. The ambient and water temperature is 25.8 and 37 degrees Celsius. The average CPU package power is 252.9 watts. Now let us try our first overclocking strategy. However, before that, make sure to locate the Clear CMOS button. Pressing the Clear CMOS button resets all your BIOS settings to default, which is helpful if you want to start your BIOS configuration from scratch. However, it does not delete any of the BIOS profiles previously saved. The Clear CMOS button is located on the rear I/O panel. In our first overclocking strategy, we make use of GIGABYTE's highly advertised instant 6 GHz profile. We unleash the Turbo Boost 2.0 power limits and enable Intel XMP 3.0. Intel Turbo Boost 2.0 allows the processor to run faster than the base specification. It does this when the processor is operating within thermal, power, and current specifications. The Turbo Boost algorithm works according a proprietary EWMA formula, which stands for exponentially weighted moving average. There are 3 parameters to consider. Power limit 1 or PL1 is the threshold the average power won't exceed. Historically, this has always been set to Intel's advertised TDP. PL1 should not be set higher than the thermal solution cooling limit. Power limit 2 or PL2 is the maximum power the processor can use for a limited amount of time. Tau in seconds is the time window for calculating the average power consumption. The CPU reduces the CPU frequency if the average power consumed is higher than PL1. Obviously, Turbo Boost 2.0 is available on Raptor Lake CPUs as it's the primary driver of performance above the base specifications. Similar to Alder Lake, but a significant change from any previous Intel Core processor is that, at least for the K-SKU CPUs, PL1 is by default equal to PL2. This change effectively means that Intel has enabled near unlimited peak turbo by default. For the 13900K, the maximum power limit is set at 253 watts. Adjusting the Turbo Boost power limits is, strictly speaking, not considered overclocking. And that's because we don't change any of the thermal, voltage, or frequency specifications of the CPU. Intel provides the Turbo Boost parameters to motherboard vendors and system integrators to make sure that their products enable the base performance of the CPU. But of course, better motherboards, better thermal solutions, and better system designs will unleash peak performance for a longer period of time. In a press release from October 21st, 2022, GIGABYTE announced the instant 6 GHz technology as an exclusive feature of their Z790 motherboards to unleash more performance from the Core i9-13900K processors. While GIGABYTE does a good job avoiding the comparison with the teased 6 GHz Core i9-13900KS, one cannot help but make the comparison. However, assuming the Core i9-13900KS processor extends the thermal velocity boost frequency by 200 MHz, GIGABYTE's instant 6 GHz technology should provide slightly higher performance than the KS. The technology increases the Turbo Boost Max 3.0 frequency for the favored cores from 5.7 GHz to 6 GHz. Thus, it allows for a 6 GHz boost, even if the CPU temperature is above the 70 degrees Celsius thermal velocity boost threshold. Intel Extreme Memory Profile, or XMP, is an Intel technology that lets you automatically overclock your memory with the objective of having more performance. It is based on the JEDEC specification, and it allows memory vendors such as G.Skill to program higher performance settings onto the memory sticks. Intel Extreme Memory Profile 3.0 is the new XMP standard for DDR5 memory. It is primarily based on the XMP 2.0 standard for DDR4, but has additional functionality. There's a lot more to the new XMP 3.0 standard that is outside of the scope of this video. If you want to learn more about XMP 3.0, please have a look at my Alder Lake launch video. Upon entering the BIOS, in easy mode, click XMP Expo Disabled. Switch to Advanced mode. Set CPU upgrade to instant 6 GHz, then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. Since we're not pushing the clocks that much higher than stock, the 6 GHz only affects up to 2 active P-cores, we don't expect that much improvement in performance. That said, improving the memory performance by using XMP 3.0 does help in memory-sensitive benchmark applications. We see the highest performance improvement of plus 10.69% in Geekbench 5. When running Prime 95 small FFTs with AVX2 enabled, the average CPU P-core clock is 5033 MHz and the average CPU E-core clock is 4199 MHz with 1.213 volts. The average CPU temperature is 100 degrees Celsius. The ambient and water temperature is 27.6 and 42 degrees Celsius. The average CPU package power is 317.4 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU P-core clock is 5350 MHz and the average CPU E-core clock is 4300 MHz with 1.309 volts. The average CPU temperature is 100 degrees Celsius. The ambient and water temperature is 27.4 and 41 degrees Celsius. The average CPU package power is 325.4 watts. In our second overclocking strategy, we rely on GIGABYTE's Enhanced Multi-Core Performance Profile. Enhanced Multi-Core Performance, or EMCP, is one of the 4 automatic overclocking profiles on the GIGABYTE Z790 motherboard BIOS. Unlike the instant 6 GHz profile, which we used in OC strategy number 1, it does not increase the maximum turbo boost frequency. Rather, it makes sure that all the P-cores can run up to the maximum default turbo boost frequency, which is 5.8 GHz on this Core i9-13900K. Upon entering the BIOS, in easy mode, click XMP Expo Disabled. Switch to Advanced mode. Set Enhanced Multi-Core Performance to Enabled, then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. With EMCP, we increased the processor P-core significantly over the stock settings from 5.5 GHz to 5.8 GHz in all core workloads. Therefore, we expect a significant performance uplift, especially in multi-threaded benchmarks. However, the voltages required for 5.8 GHz are pretty high. Thus, in all-core workloads, the CPU hits TJ max much more quickly than before. So, in benchmarks like Cinebench R23, we see that the performance is slightly lower than stock. We have the best performance improvement of plus 12.31% in AI benchmark. When running Prime 95 small FFTs with AVX2 enabled, the average CPU P-core clock is 4926 MHz and the average CPU E-core clock is 3829 MHz with 1.244 volts. The average CPU temperature is 100 degrees Celsius. The ambient and water temperature is 25.8 and 40 degrees Celsius. The average CPU package power is 289.2 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU P-core clock is 5162 MHz and the average CPU E-core clock is 4027 MHz with 1.331 volts. The average CPU temperature is 100 degrees Celsius. The ambient and water temperature is 25.8 and 40 degrees Celsius. The average CPU package power is 296.4 watts. In our third overclocking strategy, we will pursue a simple manual overclock. At least, that was the plan. As it turns out, this simple overclock turned out to become quite an in-depth overclock. So rather than how I usually approach this manual overclocking strategy, I won't go over the list of the technologies and then say what I changed. Rather, I'll first cover the theory of overclocking the Core i9-13900K and then show a more practical example of how I went about using those technologies on my specific system. On Raptor Lake, the VCC-IA voltage rail drives the voltage for the CPU cores, P-core and E-core and the ring. That means a single voltage is used for all these parts of the CPU. How we configure that voltage is both straightforward yet complex. There are three key aspects to understanding how voltage is configured on Intel platforms: the CPU, the motherboard design, and the voltage regulator. Let's start with the CPU side of the story. An Intel CPU relies on a lot of factory-fused voltage frequency curves, or VF curves, to manage its dynamic performance behavior. A VF curve essentially describes the relationship between an operating frequency and the voltage required to run that frequency stably. A lot of parts inside your CPU have a VF curve, including those that affect the VCC-IA voltage rail. In case of the Core i9-13900K, the VCC-IA voltage rail is affected by no less than 13 different voltage frequency curves. Based on these VF curves, to get a specific voltage provided via the VCC-IA voltage rail, the CPU issues an SVID request to the voltage controller. The VID requested is the highest among all the requested voltages according to every voltage frequency curve affecting the voltage rail. Let's take an example. The highest voltage requested according to the relevant VF curves is 1.4 volt by P-core 0. That would be the VID request to the voltage controller. Here's another example. The highest voltage requested according to the relevant VF curves is 1.3 volt by the ring. That would be the SVID request to the voltage controller. The goal of the SVID request from the CPU to the voltage controller is to make sure that the voltage requested by the CPU according to its voltage frequency curves matches the effective voltage at the CPU die. But overclockers and enthusiasts know very well that's not always the case. And that's because there are a lot of electrical components between the voltage controller and the CPU. To manage this challenge, we essentially have two tools: AC/DC load line and VRM load line. The AC/DC load line is a tool that allows motherboard engineers to bring into the equation of the CPU voltage frequency curve also the motherboard electrical impedance. Electrical impedance can significantly affect the effective voltage at the CPU die. Therefore, there may be a significant difference between the requested and effective voltage. We can define the AC/DC load line parameters to account for this difference. Adjusting the AC load line offsets the requested voltage defined by the factory-fused voltage frequency curve to account for any electrical impedance. For example, suppose we know that a 1.4 volt voltage output by the voltage controller, as requested by the CPU, results in an effective voltage of 1.35 volt at the CPU die due to electrical impedance. In that case, we can configure the AC load line such that the CPU requests 1.45 volt instead. Adjusting the DC load line informs the CPU about the expected effective voltage at the CPU die. For example, suppose the voltage frequency point is 1.4 volt, but we've configured the AC load line such that it's bumped up to 1.45 volt. If we don't tell the CPU that a 1.45 VID request results in a 1.4 volt effective core voltage, then the CPU assumes the effective voltage is 1.45 volt. That will skew any power management metrics that rely on the VID information. Before we dig into setting up the AC-DC load line, we must first talk about the VRM load line. The VRM load line is essential for two main reasons: the V-droop and undershoot. V-droop is the decrease in voltage when the CPU goes from idle to load. You want your CPU to be stable in all scenarios, so knowing the lowest voltage the CPU runs at is very important. After all, if the voltage is too low, the overclock won't be stable. Undershoot and its counterpart overshoot is a brief voltage spike that occurs when the CPU switches from idle to load or from load to idle. These spikes cannot be measured easily and usually require an expensive oscilloscope to detect. I highly recommend the Elmo Labs article titled VRM Load Line Visualized to see a great picture of undershoot and overshoot in action. While undershoot and overshoot are very temporary spikes, an undershoot that's too low can still cause instability. There are two main ways to configure the voltage for the CPU cores: adaptive mode and override mode. Override mode specifies a single static voltage across all ratios. It is mainly used for extreme overclocking purposes, where stability at high frequencies is the only consideration. Adaptive mode is the standard mode of operation. In adaptive mode, the CPU relies on the VF curves to set the appropriate voltage for the VCC-IA voltage rail. Both override and adaptive mode settings are configurable via the CPU registers. So, in effect, we control the CPU VID request to the voltage controller. That's Intel's intended way of overclocking. Of course, most voltage controllers also allow independent configuration. However, for this guide, let's ignore the capabilities of the voltage controllers and focus on Intel's intended way of overclocking. We can specify a voltage offset for override and adaptive modes. Of course, this doesn't make much sense for override mode. If you set 1.35 volt with a 50 mV offset, you might as well just set 1.4 volt, but it can be helpful in adaptive mode as you can offset the entire VF curve by up to 500 mV in either direction. As I mentioned, Intel offers great granularity for tuning the many VF curves inside the CPU. Let's forget about the E-cores and ring to keep things simple and assume a case where we set a global adaptive voltage for the CPU P-cores. Now let's dig into what happens when we set a global adaptive voltage. First, disregarding any user set global or VF points offset, the adaptive voltage set in the BIOS is mapped against what's called the OC ratio. The OC ratio is the highest ratio configured for the CPU. When you leave everything at default, the default maximum turbo ratio determines the OC ratio. In the case of the 13900K, that ratio is 58x, which is the thermal velocity boost frequency. When you manually overclock, the OC ratio is the highest ratio you configure across all the settings and options. Second, specific rules govern what adaptive voltage can be set. The voltage set for a given ratio n must be higher than or equal to the voltage set for ratio n-1. Suppose our 13900K runs 58x at 1.45 volt. In that case, setting the adaptive voltage mapped to 58x lower than 1.45 volt is pointless. 58x always runs at 1.45 volt or higher. Usually, BIOSes allow you to configure lower values. However, the CPU's internal mechanisms override your configuration if it doesn't follow the rules. The adaptive voltage configured for any ratio below the maximum default turbo ratio is ignored. Take the same example of the 13900K specified to run 58x at 1.45 volt. Suppose you try to configure all cores to 55x and set 1.45 volt. In that case, the CPU ignores this because it has its own factory-fused target voltage for all ratios up to 58x and uses this voltage. You can only change the voltage of the OC ratio, which, as mentioned before, on the 13900K is 58x and up. For ratios between the OC ratio and the next highest factory-fused VF point, the voltage is interpolated between the set adaptive voltage and the factory-fused voltage. Returning to the example of the 13900K specified to run 58x at 1.45 volt, let's say we manually configure the OC ratio to be 62x at 1.5 volt. The target voltage for ratios 59x, 60x, and 61x is now interpolated between 1.45 volt and 1.5 volt. So in conclusion, the adaptive voltage that you set in the BIOS maps against what's called the OC ratio. Unless explicitly programmed, the OC ratio is the highest programmed ratio for the CPU cores across all of your settings. That include the by-core usage, per-core ratio limit, OCTVB, and so on. For ratios below the OC ratio, the voltage is determined by their factory-fused voltage frequency point, or if there is no VF point, interpolated between the next and the previous voltage frequency point. Advanced voltage offset, more commonly known as the VF points, is an extension of adaptive voltage mode, as it exposes some of the points of the factory-fused voltage frequency curve to the end user. The main purpose for the VF points is that it allows the end user to undervolt or overvolt specific points on the voltage frequency curve. Overclockers and enthusiasts most commonly use the VF points in two main ways. First, you configure a positive voltage offset for the highest VF point, which helps achieve a higher single-threaded overclock frequency. Second, you configure a negative voltage offset for the second highest VF point. That helps achieve lower voltage for all-core boost, which results in a lower temperature in all-core boost and thus potential additional overclocking headroom. On Raptor Lake, there are 15 distinct voltage frequency points. However, only points 1 to 11 are in use. Furthermore, some points can be copies of other points. On the 13900K, the VF points are as follows. VF point 7 matches the Turbo Boost 2.0 frequency, VF point 8 matches the Turbo Boost Max 3.0 frequency, VF point 9 matches the Thermal Velocity Boost frequency, and VF point 11 matches the OC ratio. VF point 10 is a copy of VF point 9. Ideally, we would now adjust the VF curve with the following modifications. Offset VF points 7, 8, and 9 with a negative value to undervolt the CPU. That reduces the effective voltage when the CPU reduces the frequency in extreme workloads, resulting in higher average frequencies. Offset VF point 11 with a positive value to overvolt the CPU. That enables additional frequency headroom, allowing us to push the CPU frequency higher in single-threaded or light workloads. Lastly, unfortunately, the implementation of the VF points on Raptor Lake is not that mature yet. There are a couple of challenges that make it difficult to use it for a daily overclock. Two problems in particular gives us the biggest headaches. One, sometimes the VF points don't work correctly in combination with 100 MHz BCLK. An easy workaround is to have the BCLK frequency slightly lower or higher than 100 MHz. Two, sometimes programming VF point 9 conflicts with VF point 10. The easy workaround is to program both VF points to the same value. Also, sometimes motherboards have auto rules that automatically set an adaptive voltage when end users set high CPU ratios. It's important to know that VF point 11 adds on top of the adaptive voltage. If you're not careful and leave the adaptive voltage set at auto, you may end up with a really high voltage. The easy workaround here is to set the adaptive voltage manually. Now that we know how the voltage is configured on a Raptor Lake CPU, let's have a look at how the ratios are configured on Raptor Lake CPUs. Generally speaking, there are two ways to set ratios on an Intel CPU: sync all cores or by core usage. Sync all cores sets a single fixed ratio applied to all cores, which is very much the historical way of Intel CPU overclocking. Turbo ratio configuration allows us to modify the default Intel frequency specification and configure an overclock for various scenarios. There are three essential elements to understand any turbo ratio configuration. 1. You can configure the maximum allowed CPU core ratio for any number of active cores. 2. You can configure the maximum allowed CPU ratio for a given CPU core. 3. The turbo ratio configuration for P-core and E-cores is independent. To explain the first point, let's take the default configuration of the 13900K. The 13900K has a total of 8 P-cores. Therefore, we can configure the maximum allowed P-core ratio for when 1 P-core is active, when 2 P-cores are active, all the way up to when 8 P-cores are active. To explain the second point, let's again consider the 13900K specification. The 13900K has 8 P-cores, 2 of which can boost 300 MHz higher than the other 6. Those cores are called the favored cores and are part of the Turbo Boost Max 3.0 technology. In my Rocket Lake launch video, I highlighted that Intel had introduced a new overclocking tool called per core ratio limit. This technology is also available on Raptor Lake. It allows us to set a maximum ratio for each P-core individually. To explain that third point, again, let's refer to the 13900K specification. The CPU has a total of 8 P-cores and 16 E-cores. The P-core rules for maximum allowed frequency also apply to the E-cores. However, with one major caveat. The E-core CPU ratio can only be controlled in groups of 4 E-cores. So for the 13900K, since it has 16 E-cores in total, we can configure the maximum allowed core ratio for a total of 4 groups of 4 E-cores. However, we can still configure the maximum allowed frequency for 1 active E-core up to 16 active E-cores. AVX negative ratio offset is a feature that allows you to decrease the frequency when AVX instructions are detected. Essentially, it's a tool that allows us to maximize the frequency in both SSE and AVX workloads. While the feature has been on Intel CPUs for quite some time, since Alder Lake, the behavior of the AVX negative ratio offset has changed a little bit. Here are the key things to know. First, on Raptor Lake, the AVX negative ratio offset is only applied to the P-cores. The E-core frequency is unaffected. Second, by default, the maximum ratio during an AVX workload is the Turbo Boost 2.0 ratio. If you want an offset of 0, so AVX workloads don't reduce the frequency, you'll need to manually set 0. Third, the AVX negative ratio offset is referenced against each core's maximum ratio limit, since Raptor Lake supports per P-core ratio control. That is important if you're using the per core ratio limit function to restrict the worst cores from boosting to the maximum frequency. Lastly, Intel has changed how it flags an AVX workload. The effect is that some light AVX workloads will no longer trigger the AVX negative offset. We can demonstrate this new behavior using yCruncher. We used yCruncher component tester to test various AVX workloads on the 13900K. 4 of the 6 pure AVX2 workloads trigger a frequency reduction when an AVX negative ratio is set. For the 2 other workloads, the frequency remains elevated. Now that we know everything there is to learn about voltages and ratios on the Core i9-13900K, let's begin our simple overclock. I overclock my CPU with the following steps. The main priority is maximizing the P-core frequency in all core workloads. The second priority is maximizing the P-core peak frequency in single core workloads. The final priority is ensuring our configuration is stable in AVX workloads and under transient conditions. But before we can change the ratios, we first have to set up the VCCIA voltage controller. As I already highlighted in the previous segment, setting up the VCCIA voltage controller is an essential part of overclocking with the Z790 Aorus Master motherboard. By default, the motherboard uses an elevated AC load line and a very steep VRM load line, and that has the following effects. 1. When the CPU issues the SVID request to the voltage controller, it offsets the factory-fused voltage frequency curve with additional voltage. This results in higher voltage requested to the voltage regulator and higher voltage output to the CPU. 2. As the workload increases, the voltage regulator outputs a lower voltage due to the steep VRM load line. That lowers the effective voltage in an all-core workload, thus lowering the temperature and possibly increasing the frequency under load. When we pursue a manual overclock, we want to control the CPU voltage frequency curve as perfectly as possible. So the first thing we need to do is make sure that the voltage requested from the CPU to the voltage controller is according to our custom designed voltage frequency curve and not deviate from it. So I set the following configuration. The AC load line setting ensures the CPU issues its SVID voltage request to the voltage regulator precisely according to the voltage frequency curve. The VRM load line setting I found, after some testing, most suitable to ensure the voltage did not drop under load. The DC load line setting tells the CPU that the effective core voltage does not deviate from the requested voltage. The next step is to figure out what is this particular CPU's default voltage frequency curve. In SkatterBencher number 31, I covered the VF curve for all the Lake CPUs in quite a bit of detail. Since Raptor Lake is very similar to Alder Lake, we can use the same techniques to extract the voltage frequency curve of this Core i9-13900K. In addition to the P-Core VF curve, I extracted the E-Core and Ring VF curves, which turned out to be very important when we start tuning the CPU. As you can see, the E-cores require substantially more voltage at significantly lower frequencies than the Ring and P-cores. If we ran all parts at 4 GHz, the SVID request to the voltage controller would be 1.255 volt as determined by the E-core VF curve. As you can see, that is almost 300 mV higher than what the P-cores would need for 4 GHz. Now that we have all the puzzle pieces in place, let's get going with our simple overclock. My target for the P-cores is to run 5.6 to 5.7 GHz in a Prime 95 all-core non-AVX workload. According to the factory-fused voltage frequency curve, the voltage is 1.382 volt for 56X and 1.410 volt for 57X. To tune the voltage for 57X, we can rely on VF.8. Still, we must know that lowering VF.8 affects the interpolated voltages for 55X and 56X. Furthermore, we have to consider the E-core and Ring voltage frequency curves. Suppose we could reduce the frequency for 57X by 100 mV to 1.31 volt. In that case, the VCCIA voltage is determined by the E-core voltage frequency curve, as the factory-fused voltage for the E-core maximum frequency of 4.3 GHz is 1.365 volt. So I set the initial configuration as follows. Then I simply run Prime 95 small FFTs with AVX disabled and affinity set to only the P-cores. As you'll see, you'll hit the TJ max quite rapidly, so further undervolting of VF.8 is the key here. I can undervolt 6 out of the 8 cores for my CPU to minus 75 mV. But 2 cores are struggling a lot, P-core 4 and 6. So my choice is to limit these 2 cores to a maximum CPU ratio of 56X using the per core ratio limit feature. The next step is to push our peak P-core frequency. The main decision here really is the maximum voltage that you're comfortable with. In my case, I prefer not to go over 1.45 volt. That's not much more than the maximum voltage of the factory-fused voltage frequency curve, which is 1.445 volt. As a side note, I already mentioned that each P-core has its own VF curve. In my CPU's case, 6 of the 8 P-cores have a maximum voltage of 1.42 volt, while the other 2 have a maximum of 1.445 volt. When we set the 1.45 volt adaptive voltage, we reconfigure the maximum voltage for each core to 1.45 volt. Then it's a matter of finding the maximum stable frequency for each P-core at this voltage. Generally, I use Core Cycler and Prime 95 with affinity set to 1 core to find the maximum stable frequency. I use the following settings for the initial configuration. If multiple cores are stable at your target frequency, you can always consider increasing the ratio. But be aware of the adaptive voltage rules that we covered earlier in this video. If your CPU is stable at 6 GHz with 1.45 volt and you want to increase to 6.1 GHz, you have to be aware that the voltage for 60X will now be interpolated between 61X and 58X. So maybe your CPU will be stable at 6 GHz, 1.45 volt, and also stable at 6.1 GHz at 1.45 volt, but it won't be stable at the interpolated voltage between 61X and 58X. For my CPU, I find that all cores can pass 6 GHz at 1.45 volt. However, I've already decided to restrict 2 cores to boost to only 5.6 GHz due to undervolting. As I already explained, on modern Intel CPUs there are 3 aspects to tuning your overclock for AVX workloads. 1. All-core AVX workloads that don't trigger the AVX negative ratio offset. 2. Few core AVX workloads that don't trigger the AVX offset. And 3. AVX workloads that trigger the AVX offset. For this particular OC strategy, there are 4 challenges with AVX workloads. 1. Cinebench R23 does not trigger the AVX negative ratio offset despite using AVX instructions. That means we must make sure the voltage frequency curve is tuned for AVX stability. 2. AI benchmark triggers the AVX negative ratio offset. However, due to the dynamic nature of this benchmark, it's vital to ensure our AVX negative offset configuration accounts for the fact that it's offset from the per core ratio limit. 3. The Prime 95 AVX all-core stability test also triggers the AVX offset. Therefore, we must ensure the ratio is set to be stable for this workload. In addition to the question what AVX and what non-AVX frequency you can run, you also have to consider that a dynamic workload that switches between AVX and non-AVX workloads can cause quite a stressful transient condition. So while you may be stable at your non-AVX frequency and stable at your AVX frequency, switching between those frequencies might be unstable. Unfortunately, it's very difficult to really test whether your CPU is stable in all configuration, and it really boils down to going through your benchmarks and going through your stress tests and just checking if your CPU can pass all those different dynamic scenarios. In my overclock, I use an AVX negative ratio offset of -2 to deal with the AVX workloads. Upon entering the BIOS, in easy mode, click XMP Expo disabled. Switch to advanced mode. Set CPU base clock to 99.85 MHz. Enter the advanced CPU settings submenu. Set voltage reduction initiated TVB to disabled. Set AVX settings to user defined. Set AVX offset to 2. Set active turbo ratios to manual. Set turbo ratio 1 P-core to 4 P-core active to 60. Set turbo ratio 5 P-core and 6 P-core active to 59. Set turbo ratio 7 P-core active to 57. Set turbo ratio 8 P-core active to 56. Set turbo E-core ratio 1 to 44. Set turbo E-core range 1 to 16. Set turbo per core limit control to manual. Set turbo P-core 0, 1, 2, 3, 5, and 7 to 60. Set turbo P-core 4 and 6 ratio limit to 56. Leave the advanced CPU settings submenu. Set V-core voltage mode to adaptive V-core. Set VF offset mode to selection. Set internal CPU V-core to 1.45. Set VF point 6, 7, 8, 9, and 10 offset to -50 mV. enter the Advanced Voltage Settings submenu. Enter the CPU VRM Settings submenu. Set CPU vCore load line calibration to Turbo. Enter the Internal VR Control submenu. Set IAAC load line to 1. Set IADC load line to 1. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. We don't push the operating frequencies much higher than stock. Furthermore, we rely primarily on undervolting opportunities to squeeze more performance out of our CPU in all core workloads. Generally, the performance improvement is not spectacular. Still, we get a performance uplift of up to plus 12.73% in AI benchmark. When running Prime 95 small FFTs with AVX2 enabled, the average CPU P-core clock is 5227 MHz and the average CPU E-core clock is 4051 MHz with 1.221 volts. The average CPU temperature is 100 degrees Celsius. The ambient and water temperature is 26 and 39 degrees Celsius. The average CPU package power is 331.6 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU P-core clock is 5492 MHz and the average CPU E-core clock is 4287 MHz with 1.319 volts. The average CPU temperature is 100 degrees Celsius. The ambient and water temperature is 26 and 39 degrees Celsius. The average CPU package power is 337.1 watts. In our fourth and final overclocking strategy, we rely on advanced tuning features to squeeze more performance out of our CPU. Specifically, this time around, we'll use overclocking thermal velocity boost. In 2018, Intel introduced thermal velocity boost with the Core i9-13900K mobile Coffee Lake processor. It's since been an indispensable feature on Intel Core processors. Intel Thermal Velocity Boost does two things. First, it decreases the operating voltage if the CPU temperature is below the TJ max. 2, it opportunistically increases the clock frequency above the Turbo Boost 2.0 and 3.0 frequencies if the CPU operates below a part-specific temperature threshold. This threshold is usually 70 degrees Celsius on desktop CPUs. With the introduction of the Intel cryo cooling technology in 2020, Intel opened up the TVB configuration to motherboard vendors. The feature is named Overclocking Thermal Velocity Boost, or OCTVB for short. The easiest way to think about OCTVB is that you're limiting or clipping the maximum turbo ratio based on the CPU operating temperature. OCTVB is based on the bi-core usage turbo ratio configuration. For each number of active cores, you can define 2 temperature points, each with a unique number of downbins. A downbin is essentially the number of ratios you want to drop. Let's take the configuration of this OC strategy as an example. When one P-core is active, the base ratio is 61x, so the frequency is 6.1 GHz. However, when the temperature is 80 degrees Celsius, the ratio is clipped by 1x. That means the maximum ratio is now 60x. When all 8 P-cores are active, the base ratio is 59x, so the frequency is 5.9 GHz. However, when the temperature is 70 degrees Celsius, the ratio is clipped by 2x. That means the maximum ratio is now 57x. When the temperature hits 90 degrees Celsius, the ratio is clipped once more by 1x. So the resulting maximum ratio is now 56x. Note that OCTVB is only available for the P-cores and not the E-cores. Testing an OCTVB configuration is notoriously tricky because you can't just use your normal heavy stress tests to validate stability. Instead, you have to rely on running your benchmark suite back to back to see if your CPU can pass all of those different scenarios. However, there is one way how we can get started with OCTVB tuning, or at the very least, how we can have an idea what our configuration should look like. And that's by relying on the voltage optimizations part of thermal velocity boost. When the voltage optimizations are enabled, we can use hardware info to track the CPU VID request as the CPU heats up. the data collected shows an apparent increase in minimum, maximum, and average VID at a given temperature. The difference is about 50 mV for 60 degrees Celsius. When running a regression, the voltage decreases at about 1 mV per degree Celsius. Now we can combine this with the information from our VF curve. From the VF curve we use in this OC strategy number 3, we find an average of 29 mV step for each ratio increase between 54x and 60x. So we have an increase of 29 mV per CPU ratio and a decrease of 1 mV per degree Celsius. Thus, we can derive that at a given voltage, we can increase the ratio for every 29 degrees Celsius reduction in temperature. Of course, this just gives us a rough estimate, and nothing beats real-world testing. But hopefully it gives you an idea of how you can start thinking about maybe getting into an OCTVB configuration yourself. To end this OC strategy, I'll give some extra commentary on my particular OCTVB configuration. As you can see from my configuration, I only increased the maximum turbo boost frequency from 6 GHz to 6.1 GHz. However, many of the P-cores can run light workloads at 6.2 GHz with a voltage of 1.45 volt. Well, that's mainly because of the challenges imposed by the adaptive voltage mode. Unfortunately, when we set the turbo ratio configuration to boost to 62x and maintain the adaptive voltage of 1.45 volt, we slightly alter the voltage frequency curve. That's because the adaptive voltage now maps to the OC ratio, 62x, and the voltage for the points between the OC ratio and the previous VF point, 58x, is interpolated between these points. As it turns out, while many P-cores can run 6.2 GHz at 1.45 volt, they aren't quite stable at the frequencies between 5.8 GHz and 6.2 GHz. The only solution would be to increase the adaptive voltage to maintain the same voltages for 59 and 60x as we had before. While I can accept a maximum voltage of 1.485 volt for an OC ratio of 61x, an OC ratio of 62x would require an adaptive voltage of 1.515 volt. That's too much for my taste, so I settle for 61x as the maximum ratio. As you can see from the configuration, I have OCTVB point B for 1 active to 6 active P-cores configured to downbin 1 ratio at 100C. What I wanted to configure was no downbins beyond OCTVB point A. However, if I leave the point configuration at auto, it configures a downbin of 2 ratios at 100 degrees Celsius. So manually configuring a downbin of 1 ratio is the best solution. As you can see from the configuration, I have OCTVB point A for 7 active and 8 active P-cores configured to downbin 2 steps at 70 degrees Celsius. That is pretty unusual, as usually we only use single downbins. To keep it short, the reason for the aggressive 2-step downbin is stability at transient loads. When the CPU goes from idle or all-core light load to an all-core heavy workload, the voltage at 59x is too high and the CPU responds erratically. By having an aggressive downbin, the ratio at any medium load would already be 57x with lower voltage. That improves the system stability in transient loads. Upon entering the BIOS, in Easy Mode, click XMP Expo Disabled. Switch to Advanced Mode. Set CPU base clock to 99.85 MHz. Enter the Advanced CPU Settings submenu. Enter the Frequency TVB submenu. Set Frequency Clipping TVB to Core Split. Set TVB Core 1 and Core 2 temperature 0 to 80. Set TVB Core 3, Core 4, Core 5, and Core 6 temperature 0 to 75. Set TVB Core 7 and Core 8 temperature 0 to 70. Set TVB Core 1, Core 2, Core 3, Core 4, Core 5, and Core 6 downbin 0 to 1. Set TVB Core 7 and Core 8 downbin 0 to 2. Set TVB Core 1, Core 2, Core 3, Core 4, Core 5, and Core 6 temperature 1 to 100. Set TVB Core 7 and Core 8 temperature 1 to 90. Set for all TVB Core downbin 1 to 1. Set Voltage Reduction Initiated TVB to Disabled. Set AVX settings to user-defined. Set AVX offset to 3. Set active turbo ratios to manual. Set turbo ratio 1 to 4 P-core active to 61. Set turbo ratio 5 and 6 P-core active to 60. Set turbo ratio 7 and 8 P-core active to 59. Set turbo E-core ratio 1 to 45. Set turbo E-core range 1 to 15. Set turbo E-core ratio 2 to 44. Set turbo E-core range 2 to 16. Set turbo per core limit control to manual. Set turbo P-core 0, 2, 3, 5, and 7 ratio limit to 61. Set turbo P-core 1 ratio limit to 60. Set turbo P-core 4 and 6 ratio limit to 56. Leave the advanced CPU settings submenu. Set V-core voltage mode to adaptive V-core. Set VF offset mode to selection. Set internal CPU V-core to 1.485. Set VF.6 to 10 offset to -50 mV. Enter the advanced voltage settings submenu. Enter the CPU VRM settings submenu. Set CPU V-core load line calibration to turbo. Enter the internal VR control submenu. Set IA-AC load line to 1. Set IA-DC load line to 1. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. Due to the limited cases where the Core i9-13900K doesn't quickly ramp to TJ Max, there are a few benchmark scenarios where we can see a performance benefit from OCTVB. The performance result is, therefore, quite similar to the previous OC strategy. We see the maximum performance increase of plus 12% in AI benchmark. When running Prime 95 small FFTs with AVX2 enabled, the average CPU P-core clock is 5222 MHz, and the average CPU E-core clock is 4029 MHz with 1.22 volts. The average CPU temperature is 100 degrees Celsius. The ambient and water temperature is 26.5 and 40 degrees Celsius. The average CPU package power is 330.9 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU P-core clock is 5469 MHz, and the average CPU E-core clock is 4283 MHz with 1.316 volts. The average CPU temperature is 100 degrees Celsius. The ambient and water temperature is 25.5 and 40 degrees Celsius. The average CPU package power is 335.3 watts. Alright, let's wrap this up. Overclocking this Core i9-13900K was quite interesting. It's always fun to hit 6 GHz with regular water cooling, and that's sort of become the standard with Raptor Lake CPUs. That said, overclocking the Core i9 was definitely a little more trickier than overclocking the Core i7 and Core i5. And that's primarily because the Core i9 is pushed quite hard out of the box. The voltage is already quite high for that 58x thermal velocity boost, and there's also a lot more E-cores, so there's less thermal and voltage headroom. If you're looking to squeeze more performance out of your Core i9 Raptor Lake, then using the voltage frequency points to undervolt the CPU at specific points of the VF curve is the main way to do it, especially for all-core workloads. Do note that there's a lot of things that come into play when you adjust the voltage frequency curve, so be aware of all those rules and all those things that affect each other. But let's be clear, the downsides that come with the overclocking process of a Raptor Lake CPU do not outweigh the benefits. Hitting 6 GHz is so cool, and all enthusiasts and overclockers will for sure have fun trying to fine-tune their Raptor Lake CPU. Anyway, that's it for this video. As per usual, if you have any questions or comments, feel free to drop them in the comment section below. Of course, I will also put up a written version of this video on my blog if you want to read through my BIOS settings, or you want to have a look at the charts for the performance, or you want to see my Prime 95 results. I want to thank you for watching, and of course I also want to thank my patrons for the support, and see you next time.